be able to drop in very much, but hopefully see you in some of the breaks. Thank you.
Thank you. Thank you. Okay, so welcome to this second meeting of the second version of the ARA program. We're very pleased this week. The first meeting was about more of the physics aspects of what's going on in resurgence. The next meeting that we're having this week is more to do with more of the mathematical aspects of things that are happening around the field. We're very pleased if everybody is able to come this week. Lots of people have travelled literally halfway around the world in order to be here. So it's very nice to see all of you again in 3D. It's very nice that people have made the effort to be here from that point of view, and I look forward to meeting and catching up with a lot of friends here from before. This meeting has been organised, a lot of the meeting has been organised by Phil Trin down here from Bath. In case you don't know who I am, I'm Chris Howells from Southampton. And we put together, hopefully, a list of speakers that'll be of interest to people to give a state of the art of what's going on in the mathematical aspects of resurgence, or more of the applied aspects as well that's going on. So the first speaker today that we're picking up with is John Chapman from Oxford. So one of the reasons that we put all of this second version of the meeting together is that 27 years ago, when we were all a lot younger and had a little bit more hair, we sort of kicked everything off. Well, sorry. We kicked everything off and started doing work in this field. And then we felt that there was a lot of younger people now working in the field, and a lot of things had moved on. The physicists had got involved in the field in a much bigger way. And so we wanted to get all of our students together as well. And I was examining one of Phil's students in Bath on Friday, working in the field as well. So there's a whole new community coming together. But we wanted to sort of give an overview of some of the more established figures to start off with. And the first person up is John Chapman from University of Oxford, who's going to speak on the blowup in nonlinear Schrodinger equations.
Thanks, Chris. I'm disappointed that you're not in fancy dress, I have to say, actually. So this is a problem. It's going to be sort of a gentle introduction to the Beyond All Orders theme of the week. And it's a problem that I came across actually in the Newton Institute at a different program on complex variables. And Pavel Lishnikov took me aside after a talk and said, this is a problem. If you're interested in exponential asymptotics, you should work on this problem. And then about a year later, Panos Kevrakidis came to Oxford on sabbatical, and he wanted to do something, and he showed me the same problem and said, I want to do this problem, I don't know how to do it. I thought, if two people have asked me, then I should have a look at it. So I'm going to talk about the nonlinear Schrodinger equation. Now, there are probably people in the audience who know a lot more about this equation than me, so I apologize in advance if I say anything stupid. This is the equation. It has a couple of invariants. So there's the mass, which is just the integral of psi squared, and then there's the energy. And then there's also this, this variance identity, which is interesting. So if you take the time derivative of the integral of x squared times psi squared, you get this expression, which has got the energy in here. And from this, you can deduce the following. Well, not exactly deduce, but you can see the second two of these. So the first one says that if sigma d is less than 2, so the two critical parameters here are the dimension, which is d, and I've used a power nonlinearity here with exponent 2 sigma. So those are the two parameters in the problem. And it's the product of those two parameters that tells you a lot about the behavior of this equation. So the subcritical case is when sigma d is less than 2, and then it's a well-posed equation, and everything is nice, and there's no blow-up. The critical case is when sigma d is equal to 2, and then, so you can see here, if sigma d is equal to 2, this term vanishes. And so if h is negative, then this positive quantity is decreasing. And so it has to hit 0 at some point, and in order for this to be 0, the solution has to blow up, essentially. So psi has to be 0 everywhere except a set of measures 0. And because the mass is conserved, that means it's infinite in other places. Right? So h is less than 0 implies blow up. But in the critical case, if the mass is sufficiently small, then you can show that then it doesn't blow up. So h must be positive. So there's a critical value of the mass in order to get blow up. And in the supercritical case, it doesn't matter. There's no sort of minimum mass beyond which you know it's going to be all right. If the energy is negative, then the solution blows up. And this is, it's an old problem. It goes back a long way. I can't even begin to do justice to some of the history, but I've just listed a few names that I'm aware of. In particular, this early paper by Landman, Papanicolaou et al. I'm going to look at some of their results and try to put a bit of flesh on them. So there's a long history.
Let me comment because I'm here now with Prof. So first what you showed with video piano, which you showed, it was shown by Kalana in 1970.
Okay.
So it's really...
So it goes a lot further back.
Sorry for that.
If you're interested, there are reviews and books, and even these are quite old now. You know, it wouldn't surprise me if there are more recent ones as well. So this is decided to put up more of a way of an apology that I'm not going to be able to tell you what people did as I go along. I sort of put all the names up at the beginning, and I might try and highlight one or two things as I go through. Okay, so the equation has, so it's obviously got sort of trivial invariances where I can change the phase by a constant multiple, or I can set the origin of time or space arbitrarily. But it's got some non-trivial invariances as well, so I can have a uniformly translating solution as long as I move the phase and I get the same equation back again. I have a self-similar scaling as well. And then you have an extra symmetry if you're exactly at the critical case, which is usually known as a conformal symmetry, which is slightly more involved. It's a time-dependent scaling, a time-dependent similarity scaling, essentially. But this lambda has to be linear in time. So it's uniform in, it's sort of AT plus B in here. And then you have this phase thing. So I'm going to be interested in radially symmetric solutions. So I'm going to reduce to just having the Laplacian is just going to be written in terms of R. And so based on this self-similar scaling here, and really looking at this as well, but based mainly on this, if I want to look at blow-up solutions, I need to introduce this sort of stretched variable, sometimes known as a lens transformation, where you sort of do a dynamic rescaling of the space variable, but here this L is a function of time. And then I have to do the change time in the right way, and I'm also going to introduce this e to the I tau in here. And what you find is that that leads to this equation now. It's slightly more complicated equation for the transform variable. And I've written, so this L here, the derivatives of L obviously appear in the equation, but I've written this, this rate of blow-up as G, and I put a minus sign in so that G will be positive if the solution is blowing up. So I've sort of gone into similarity variables, if you like, so that steady solutions of this equation now correspond to blow-up solutions. In order to close the dynamics in this, what's sometimes known as a co-exploding frame, I have to introduce a pinning condition. And this confused me when I first heard about it until somebody pointed out the following analogy. If I have a traveling wave solution and I go to traveling wave coordinates, I've got to do something to say I'm moving with the wave. Usually you might pick one point on the wave and say I'm going to fix this to be the origin. And that's how you fix your coordinates. And you've got to do the same thing in this self-similarity frame. You've got to essentially say that I'm picking one point to be fixed so that I'm blowing up with the solution. And you can do that in lots of different ways. You can apply any sort of linear constraint. The way I'm going to do it in the numerics is just to pick the real value of this function to be a constant at a particular point in space. And that just says essentially I'm traveling with the solution as it blows up. Okay, so this is what the bifurcation diagram looks like. So let me just say that again. So here, because we've gone into these stretch variables, if I have a solution now in which G is non-zero, that's a solution which is the L is decreasing, so it's a blow-up solution. The space scale is getting smaller and the scale of psi is getting bigger. So a solution which is constant, V is independent of tau, but G is non-zero, corresponds to a blow-up solution. On the other hand, if G is 0, then L is just a constant, and all I did was the self-similar, a fixed self-similar invariant rescaling. And so that just corresponds to the original soliton solution. So you now have, when you write the problem in this way, you have a sort of bifurcation between the sort of steady solutions and the blow-up solutions. So solutions in which G is equal to 0 are non-blow-up solutions, and when G is non-zero, you get a blow-up solution. So you can look at the bifurcation diagram of this problem, and you see that, so here's I did D as 1, so this is the critical case here. So you see if you're subcritical, there are no blow-up solutions. That's what we would expect. And if you're supercritical, then you get this bifurcating branch of blow-up solutions coming out of the critical bifurcation point. In this case, sigma is equal to 2. And I'm using sigma as the bifurcation parameter here, but you could use D, and you'll see that other people have used D as the bifurcation parameter. It's a slightly unusual bifurcation diagram, this, and so the most striking thing is how vertical this branch of solutions is coming out. And at some point, I'm going to talk about exponential asymptotics, so it won't surprise you to know that this is exponential here. There's not a power law. If you had the usual pitchfork, you might expect this was a G to the half coming out here. But this is sort of e to the minus 1 over G type bifurcation. And that's where the beyond all orders is going to come in. It's also a little bit unusual in that I've indicated the stability of the branches here. So this is stable, and this is stable, and this is unstable, and this is unstable, which is a little bit weird for if you had a regular pitchfork, you'd expect both these things to be stable, right? So it's a little bit of a weird bifurcation diagram. Okay, so let me go back to this paper by Landman et al. So they drew this bifurcation diagram back in 1988 with also a very steep rise here. And in fact, they had a back-of-the-envelope calculation. They were using D as their bifurcation parameter, and their back-of-the-envelope calculation said that I think they chose sigma is equal to 1, so D is 2 as their critical value. And their back-of-the-envelope said that should be like e to the minus some constant over G divided by G. And their argument could not tell them what lambda was, and it also could not tell them the prefactor, but they could tell that this was the sort of functional form without knowing any of the constants. So they plotted G times D minus 2, the log of that against 1 over G, so the gradient of this curve should be minus lambda if they were right. And they get a very nice straight line from it. And then they fit the straight line, and their numerical value of lambda was 3.14, which is very suggestive, obviously. So what I want to do is to aim to fill in some of the flesh on this. So this is right. I want to show you, well, as others have done, lambda is obviously pi, and that's now well known. But I want to find out what the constants are here and do it in a systematic way. So I'm going to do one more transformation before I start some analysis, and that's to factor out this e to the minus ig xi squared over 4, because that's the dominant oscillation in the tail. And so this is sort of related to that conformal invariance. So the conformal invariance would be the case when this term here cancels with this term. At the critical value, this would vanish, and that means that I get back to the same equation that I had. So it turns out that if L is linear, then G prime is minus G squared, and these two terms cancel. But I'm going to be considering the I'm not going to use that conformal invariance. I'm going to be considering the case where this is not 0 and we don't have that. So my goal is to solve this equation in the limit where g tends to 0 and sigma d tends to 2. So maybe I didn't make this clear. So I introduced this g, but so I have these, I had d and sigma. Those are parameters in my problem. I'm free to choose them. But g is something that comes out in the wash, as you saw in the bifurcation diagram. That as soon as I fix my pinning condition, that's the extra scalar constraint that fixes the scalar variable g. Right? So g is not free, g is determined. And so I'm going to solve this in the limit that g tends to 0 and work out what's the relationship between sigma and g in order to, as g goes to 0. And what we will find is that g evolves exponentially slowly and that sigma d is exponentially close to the critical value, which is 2. And that means that, well, it's not very red on here, but that means I can more or less ignore, to begin with, the solutions evolving exponentially slowly, so I don't need to worry about this. G prime is exponentially small, and sigma d minus 2 is exponentially small. So I'm going to throw away those 3 terms to start with. I'll bring them back in later and just look at what happens to the rest of the equation. So before I sort of dive into some formulae, let me give you a schematic of how it's going to work. So this is the leading order solution is just the usual soliton solution. So I have my soliton, and it's got exponential decay in the far field. And I'm going to generate a perturbation expansion of the soliton solution because there's a sort of extra term that generates a full asymptotic series. But then in the far field, this exponential decay has, at some point, there's a turning point, and it switches from exponential decay to oscillating exponentials. And it turns out at infinity that if you want finite energy, you're only allowed one of the 2 possible oscillating exponentials. Essentially, the phase of this oscillation is fixed. And that means that this turning point has to have an exponentially small reflection going the other way. And that exponentially small reflection comes and interacts with the soliton, and that gives you the condition that determines the bifurcation, the normal form. So that's where it's a sort of, it's beyond all orders, but I'm not going to have to go into the complex plane because it's a sort of turning point. So I feel a little bit embarrassed about that in this audience. But as I say, it's a nice, gentle introduction. OK, so let me sort of flesh that out a little bit for you. So in the near field, I'm just going to do a regular power series expansion. I have to introduce this slowly varying phase factor out the front. I forgot about that to start off with, and it took me ages to work out that I had to put it in. And that's the thing that enables you to satisfy the pinning condition. So that's why I forgot about it, because if you forget about pinning, you can sort of forget about this and just know that you're choosing some solution. But if you really want to compare with numerics and you say, I've pinned it this way numerically, then you have to introduce this function to allow you to do the pinning. But it's going to vary exponentially slowly, so it's not going to really play a role. So the nice thing about that extra transformation I did is that once you throw away the exponentially small terms, everything is basically real. So I don't have to worry about complex solutions until I get to the far field. So at leading order, I just get the usual nonlinear Schrodinger equation, the solution of which is just the critical ground state soliton. So I've kept d and sigma arbitrary to show you that it doesn't really matter which one I vary. But if you choose, for example, d is 1, which is nice and easy, because in 1d you don't have any of these 1 over xi terms, then the solution here is just the square root of a sec. So that's very well known, straightforward. And then at next order, you're going to get you get a full expansion here, because there was one term that was g squared psi squared v in the equation, so that's going to now be a forcing term for v1, and you keep going. So I should point out here, so there is a solvability condition on this equation. Well, if I made it to be the full range instead of the half range, then the derivative of the leading order solution would satisfy this equation, as always happens. And so the derivative of V0 should, when I integrate it with the right-hand side, should give me 0. And in some problems, that is the condition that gives you the bifurcation equation, gives you the normal form. But in this problem, that's automatic, because this function is even, and the derivative of this is odd, and so it integrates to 0. So there are other problems in which that's not the case, and it's less interesting, whereas in this case, that's automatic, and that's why you have to go beyond all orders to get your solvability condition. OK, so the fact that this term is xi squared, so in the original equation, this was a g squared xi squared. So when xi is large, that term is going to jump order, and it's not going to be in the first order correction. It's going to be in the leading order equation. And that will happen when xi g is order 1. So the expansion breaks down when xi g is order 1, and I have to do a different sort of expansion there. The terms rearrange, if you like. So the leading order solution in the far field, as I said, is decaying exponentially. And that means that in the far field, I don't have to worry about the nonlinear term. It's exponentially small. So in the far field, I just have a linear equation to solve. And in a rescaled far field variable, so I rescale xi to be order 1 over g, I get this equation, where this is the term that has jumped order in the far field, but I've now lost the nonlinearity. So now I do a WKB solution of this equation in the far field, the usual sort of thing. And at leading order, you get the iconal equation, and you can work out what the decay of this exponential is. And you can see now the turning point, right? Phi prime is 0 and rho is equal to 2. So the nature, phi here is going to be real until rho is greater than 2, and then it's going to start to be imaginary, and I'm going to start to get oscillating solutions. You can work out the amplitude. That's nice and easy. And then you can do the matching. So this is the decay of the near field solution. This is what the far field solution looks like as I go back towards the near field. So you just read off the constants, and you work out what this A naught is and what the K has to be. So match them all together nicely. All right, what about beyond the turning point? So now my phase has got an I. I finally do see a complex variable. As I said, only one of the two, I could do plus or minus here, but only the plus one has a finite energy. And so I have to rule out the minus one. And so for rho greater than 2, I have some similar WKB expansion, but now I've written this as an I phi 2, where phi 2 is I've switched the order of the variables here, so phi 2 is real, and I'm integrating from 2 instead of 0. And the amplitude is very similar. So the fact that you have this turning point means you get this exponentially small reflection that goes back towards the near field. And so you can do that just by going into the turning point and doing the matched expansions, and you have an airy function locally, as you always do. So if I go local to the turning point, then I get Airy's equation, solution AI with a minus s, bi with a minus s. And then you just look at the asymptotics of the Airy functions to do the matching with the two WKB solutions. So if I'm going out of the turning point to the right, so s goes to infinity, I'm going to rho greater than 2. I only want one of these two solutions, and so I have to have lambda is I mu. So I think I want this one to cancel, so I get rid of this one. That tells me lambda is I mu. And then I can then read off what the coefficient of the exponentially small reflection is. So you have to get your head around this sometimes. So it was exponentially decaying the solution out of the near field into the far field, which means in the turning point, it's exponentially decaying towards the turning point. So as I go backwards, the base solution is exponentially growing. So this is the solution that I already had. And then this is the new one, which is going to be an exponentially small reflection going, which is going to be decaying the other way. Okay. So now in row less than 2, I have to modify my WKB expansion that I had. So before I started off, I had this e to the phi over g times this series expansion for the amplitudes. And now I've got this extra term, which is e to the minus rho. So that's exponentially decaying away from the turning point, which means as far as the near field is concerned, it was the exponentially growing solution. And you can work out what the coefficient is, and the coefficient from the matching has this e to the 2 phi 2 over g, and that's where the minus pi over g comes from, right, from this phase. So that's what you get when you have this WKB solution. It started off where the argument was 0 in the near field. You track the decay down to the turning point, and then you track the decay back again. That's where you get the that's why you get twice here, and that's why you get e to the minus pi over g. So that's the exponentially decay that you had in both regions. And so now I've got to do the matching with the near field again, not just with this term, but with the extra exponentially small term as well. And when you look at what this thing does as you go inwards now to rho is equal to 0, it's got an e to the plus rho. As I say, it's exponentially decaying that way, which means it's exponentially growing that way. So it's growing out of the near field, but it has an exponentially small prefactor because of the gamma. All right, we're almost there. I've now got to go back to the near field and match this new exponential in, and hopefully that is going to give me the solvability condition that finally gives me the relationship between sigma and g. So now I have to split my near field solution into the sort of algebraic expansion that I already have. I'm going to call that vreg, regular part. And then I've got this exponentially small correction that I'm now trying to solve for. And so I'm going to write down the equation for this exponentially small remainder. It's just obviously just the linearization of the equation around about this regular expansion. So that's just what the first line is here. Need to worry about it too much. And then I'm now going to put in all those exponentially small terms that I neglected when I was just doing the power series expansion. So I'm going to neglect doubly exponentially small terms. So I'm going to neglect the nonlinearities applied to Vx. So I'm not going to have any Vx to the 5 terms or anything like that. But if you keep exponentially small terms but not the doubly exponentially small terms, this is what you get. So you get terms due to the fact that d is not exactly at dc and sigma is not exactly at sigma c. You get these derivatives of g that I said were exponentially small and phi, and you get this d sigma minus 2 term that I said was exponentially small. So this is the stuff that's all on the right-hand side. And now there's a solvability condition on this equation. And to work that out, I'm going to write it in terms of real and imaginary parts. And it turns out there's no solvability condition on the real part. You can always satisfy that equation. But there is a solvability condition on the imaginary part. And that's because it's the left-hand side of the equation, the imaginary part of the left-hand side of the equation, is satisfied by the regular, by vreg, essentially. And the reason that's true is because of phase invariance. Essentially, I started off with an equation, and I'd scale it so that the solution was real, but I know that I have an invariance where I can arbitrarily add a constant amplitude. And this is, if I just add a sort of epsilon amplitude, then the perturbation to the solution would be in the imaginary part and would be equal to vreg. So it sort of has to be true that that was going to satisfy that equation. So now I need to write down the imaginary part of this equation. I multiply by the regular solution, and I integrate, and then the left-hand side is going to disappear, and I have a solvability condition on the right-hand side. So you can see what the important terms are going to be. I'm only interested in the imaginary components here. So it's this term here, and it's this term here. Everything else is going into the real part. So when you do that, this is what you get. So here are those two terms multiplied by the reg. And when the left-hand side, I said, it disappeared. I said that a little bit too quickly. So I integrate the left-hand side by parts, essentially, and I do get the boundary terms left. So this is what comes out of the boundary terms when I integrate the left-hand side by parts. And so these boundary terms I'm going to evaluate by matching with the exponential solution that I've just worked out. Because the regular expansion is decaying exponentially as I go outwards. But remember, this new exponentially small term is growing exponentially as I go outwards, because it was decaying from the turning point. So it's growing as I go out. And they have exactly the right sort of growth and decay so that they cancel with each other here. So I can evaluate the left-hand side by matching as r tends to infinity. I know what the limit of this regular part is. That was just a0 e to the minus r. And I've just worked out that this thing, as I went inwards, had an e to the plus r times an a0 times the imaginary part of this gamma. So I can evaluate this left-hand side by matching with my far-field solution. And you just get 2 times a0 squared times the imaginary part of this gamma, which, remember, is the exponentially small coefficient that we worked out. And for the right-hand side, well, that's nice and easy. That just involves the regular asymptotic expansion. So you can basically work that out. And in fact, this is just the time derivative of this one. And so you basically need a good approximation for the integral of the square of your base solution. You need, because the only time dependence is through the fact that g is actually time dependent, it's not enough just to work out the first term here. You need the second term, because the first term is independent of tau. So the second term is what gives you the a contribution from this. So when you put that all in, this is the equation that you get. So this is the equation that's the solvability condition that finally tells you what g has to be in order to get a solution to the equation. And so you can see it's a first-order differential equation for g, which is, as I said, time-dependent. It has the sigma d minus 2 coming out from that term in the solvability condition, and then it has the e to the minus pi over g that came out from the gamma, the exponentially small thing that we matched to. And we know what all these coefficients are. We just worked them out in terms of the base solution. I said that I was doing g positive, but when I showed you this diagram, I also showed you some g negative. So you can do exactly the same thing when g is negative. You've got to be a little bit careful about which solutions are allowed. And the upshot is that you get a sine of g in here, and you get a mod g in here. So when g is negative, you don't get any exponentially large terms. You get e to the minus pi over mod g. So this is now valid for both positive g and negative g. And so you get a branch up here of steady solutions corresponding to d sigma minus 2 is, well, you can see it's e to the minus g divided by g. It's exactly what Papanicolaou et al. Said it should be, with the pi and the coefficient determined. And the natural bifurcation parameter here is d sigma minus 2. So you see it doesn't really matter. They were varying d. I showed you varying sigma. It doesn't really matter which one you vary. It's d sigma that's the key parameter. And we've picked up not only the steady states here, but also the evolution problem, right? I could start this so it tells me not just which state is stable or not. So this already tells me the stability of these branches here. But it also tells me how I would evolve to approach the blow-up solution. And this is validation, if you like, of the results. So again, I've plotted the log of g of times sigma minus 2. I did it in d is equal to 1 because it's much easier to do the numerics, against 1 over g. So this should be the straight line. I haven't flipped the sign, so that's why mine goes this way. This is two curves plotted on top of each other. The one at the back is red and it's slightly thicker, and the one at the front is black. So that's why that looks like, well, my screen, and you can sort of see the red outline of the black. They essentially lie on top of each other. But it is I'm never that impressed when people show plots on log scales, right? It's quite easy to get things looking close on a log scale. There are also, you see these undulations here, that it sort of oscillates as you get down here. That is not numerical error. You can see that both curves oscillate, so I will explain that oscillation to you. That was seen in some earlier works and not really commented on. I'll explain where that comes from. All right, so I'm going to flick through it now. I want to show you some comparison with numerics to show you how good that approximation is, but I want to just tie it in with one or two other things first. So one thing that's well known about this equation is that if you're supercritical, then the collapse is like square root of t. The blow-up goes like 1 over t to the half. But if you're critical, then it's not like that, and you get an extra factor of log t. And I just want to show you that that is built into the equation that we've derived. So if I go to the critical case, so I put sigma d is equal to 2, so this describes the evolution of g. So essentially, if g is minus L tor over L, then you can work out that, so I integrate that up, and that tells me that log L looks like the integral of g. And then I can write that instead of d by d tor in terms of d by dg, just using my equation. So that tells me that log L should go like the integral of g, integral over g of g squared e to the pi over g. So I can do the asymptotics of that, and that gives me g4 e to the pi over g. So that tells me that g will go like pi over log of minus log of L. And then I can go and see what's the relationship between tor and L. And so from this equation, which was the definition of tor, t is looking like the integral of L squared. And I write that in terms of d by dl. So that's looking like the integral of L over g with respect to L. And then I just worked out that g was 1 over log L. So this is where you get L squared, log of 1 over L. And so that's why you get that L squared goes like t over log. It's sort of built into that equation. So as Pavel pointed out in one of his papers, this log is so weak that you have to have unrealistically large amplitudes if you ever see it. You're never going to see this in practice. But this equation works perfectly fine for even moderate amplitudes. So if you don't do the large tor asymptotics of this, but you just solve this equation, then it's fine. In the numerical comparison, I want to include a few higher order terms. So I just want to show you how far you can sort of push this now you know what's going on. So this solvability condition that I had this regular expansion in. And I can calculate more than one term in this. So I could, in principle, generate a whole power series expansion for this coefficient and for this coefficient. And in principle, I can do the same on the right-hand side. So I had this g to the k as my scale factor here. But in principle, there should be, again, a power series expansion independent of this power series expansion in front of the whole thing. And so if you could work out what this kappa of g was, then you could get this, essentially you can get this equation to arbitrary order. So the left-hand side here is easy to do because that's just turning the crank on the inner solution and getting a few terms in the expansion. You can do the first 1 or 2 analytically, and then you get some integrals that, well, maybe you can do it analytically, but I just crunch them numerically. But you can basically get as many as you want in here. This one's a bit harder because to work out what this kappa is, so you need to work out a few terms in the amplitude expansion here, and well, you know that the more terms you go to, the more terms you get in there, so that gets a bit messy after a while. But again, it's formulaic, it's not difficult. The slightly difficult one is getting more terms in this kappa, because that comes from matching with the inner region, and to do that, you need to know the behavior as you go outwards. So the leading order solution just has an exponential decay, and then the next one has some polynomial times an exponential decay. And to get this kappa, you need to know what this coefficient is, the constant coefficient. So that is possible, but it's a little bit awkward because you've got to work through all these and just pick this one out. But we could do it, and so we generated the first 3 terms in each of those expansions. And so essentially, each of these just has a power series expansion in g squared multiplied by what I had before. And then the last thing I think I want to tell you about before I show you some pictures is why you get those oscillations. And that's due to the fact that whenever you do numerics, you're not solving on an infinite domain. Usually you just truncate it. So you have a large but finite domain. So what happens if we redo the analysis without an infinite domain but a finite domain? And I oppose, for example, a Neumann condition would be normal at the end. So I have now a condition on the far field, which is not at infinity, but it's imposed at, so if I make this size equal to k, this is rho is equal to gk. So you immediately see that I want that condition to be such that the turning point is inside the domain. So if k is not large enough, the turning point goes outside the domain, and then the whole analysis changes. But even when the turning point is inside the domain, you don't now have just one oscillating exponential outside the turning point. You've got to allow both, and the amplitude of each of them is determined by satisfying the Neumann condition at the far field. So I now have 2 oscillating exponentials, and I impose the Neumann condition, and then I take it back to the turning point and work out what happens to the coefficient of the exponential that's going back towards the near field. And you find you get this modification of what this gamma is. So this is what it was before, and this is what you end up multiplying it by, where phi 2 is just the oscillation of the WKB in the far field beyond the turning point. And this coefficient mu here is just given in terms of k and g, where k is where the boundary is. And you see this tends to 0 if k tends to infinity, because nu tends to 0. That's what you'd expect. So now you get the same equation. You just have this gamma is replaced by the imaginary part of this thing, not just the imaginary part of this. And when you work out what that is, you get this whole mess here. And it's this thing at the bottom here which is leading to those oscillations. You can see that every so often this sign, if this sign was equal to 1, then these 2 terms would cancel. And so you then use L'Hopital to work out what the value would be at that point. And it's actually growing in g at that point. So it would be a g to the minus pi over g. So these oscillations get progressively more significant as you go down. All right, let's not worry about turning point outside the domain. You can do that as well. You just have to impose the boundary condition on the far field inside the turning point. You just get a slightly different exponential now. It's not quite so strong as e to the minus pi over g, because you haven't had quite so much decay. Instead of decaying to the turning point and back, you decay to the boundary and back. So it's not quite such a strong exponential. Let's not worry about initial transients. I want to show you the numerical comparison. So this is what I showed you, the collapsing branch of the solution for d is 1, k is 50. So I said don't trust a log plot. So now I'm going to factor out the exponential. So I know it's e to the minus pi over g. So I'm going to multiply my solution by e to the pi over g and then see what it looks like. So this is what happens if I plot that not on a log scale anymore now. I've just multiplied by something exponentially small. So I've sort of exponentially blown up the axis to what I expect it to be. And the black dots here are the solution of the problem with Chapman, so I could get nice accuracy. And then the curves are what you get if you, depending on how many terms you include in those coefficient expansions. If you just choose the first term in the expansion, you get the blue. If you go to order g squared, you get the yellow. And then if you go to order g4, you get the green. And you can see that it's sort of remarkably accurate. And you see these grow, once you factor out the exponential, you see these growing oscillations due to the boundary are sort of getting worse. And I was very pleased when I saw this, that you could get this sort of level of accuracy even after multiplying by something which is exponentially large. And this is the sort of relative error in the solution of the steady state at leading order and then g squared and g4. And this is just to confirm the errors are behaving as you expect them to be. So the error in this one is going like g squared, and the error in this one's going like g4, and the error in this one's going like g6, g to the minus 6. And that's just to show you that you don't just get the bifurcation structure right, you get the solutions right as well. So this is just the real and imaginary parts of the solution in the near field and then in the far field. It shows you that they're pretty accurate. So sigma is quite close to 2, but that doesn't mean G is very big, remember, because sigma is exponentially smaller than G. So. All right, so conclusions. We have a normal form for the onset of collapse, which sort of unifies the previous analyses in either the exponent or the dimension. It captures both the log critical collapse, but also the t to the minus a half supercritical. And you get an exponentially steep bifurcating branch of collapse solutions. I looked at other problems recently, like KDV has a similar sort of structure. And it's much less interesting. So even though you get the far field decay and you get the turning point in the far field and all that looks the same, but because the solvability condition on the near field is not automatically satisfied, you already have a bifurcating branch, which is, so you get an exponentially small correction to a sort of transcritical instead of it being nearly vertical. So it's still there, but it's not so visible. And the reason it's visible here is that that solvability condition in the near field was automatic to all orders, and you needed the beyond all orders to identify it. I think I'll stop there.
John, can I take any questions?
Yeah, Pav.
Oh. So I have got a question. First for last part of your talk. So basically you got this result for small enough domain and this turning point outside, right? So as a result you're getting some intermediate asymptotic.
Is that correct, my understanding? I mean, eventually, when collapse progress, you will forget about boundary conditions.
For G sufficiently small, yes, the turning point is always outside the domain. But that depends on what your exponent is. So if you're supercritical, then there's some value of G, for example, and that's so it's not that it changes as collapse progresses.
So, but I mean, collapse shrinking, right? So in principle, turning point should also approach.
No, but a collapse, so G can be, if G is constant, that's a collapsing solution. So G will evolve until it hits its constant value, but then the original solution then is collapsing at a fixed rate then. So think of G as the rate of collapse.
Mm-hmm. Okay, and second question, just for bigger picture. So do I understand correctly that you just basically grabbed this picture of Papanikolaou and collaborators from 1988 and kind of clarified and did this more careful expansion? Is that my good understanding or not really? I mean, I'm asking.
Well, in terms of how the project, so I did this, I mean, Panos said, I want a normal form for this bifurcation, and we did the analysis to find it.
But I mean, some parts Papanikolaou already had it, right? Or you claim it's...
So in their paper, they have a back-of-the-envelope calculation, essentially, that essentially says these two things, in order to get something non-trivial, these two things have to be the same size. This one is exponentially small with some exponent, and this one is d minus 2.
Mm-hmm. Yeah, I just do not remember top of my details with Papanikolaou because it was his approach was a little special in this field.
Strange, yeah.
Mm-hmm. Thank you.
But essentially, so I think the normal form is new, but essentially lots of, as you know, it's such an old problem. Lots of aspects have been done by you as well, and part of, I guess, what we did was formalize it and make it so that it was really matching. There's been some analyses where you sort of patch at some level and things like that. So it was really to work out the full asymptotics, I guess.
Hello, John. You had a comment on stability.
Mm-hmm.
I wonder how does the arbitrariness in the choice of TC where you have the blow up, how does it show up in the stability? Yeah.
So I think that's fixed by doing this pinning, essentially. I think that's what you need to do. If you didn't do that, then you would still have that invariance. Whereas as soon as you pin your solution, everything, you're in the blow-up frame.
So you're not allowing for disturbances which would cause the
Exactly,
blow-up
exactly.
earlier
You've
on.
chosen the one which is going to blow up at that time. Yeah.
Any other questions?
Not so much of a question, but just a remark that in the KDVA equation, it has solutions with many oscillations that are asymptotically described by a NLS as well. So perhaps there is a limit where you can still use these results, non-trivial results, in the KDVA equation as well.
Okay. Thank you.
Could you make up other problems with this?
I presume so. I mean, it's slightly different to the problems. Normally, the exponentials that I get come from complex singularities, and they're oscillating always, and then they're not allowed at infinity. And if you have, or you have wave problems where you have an eigenvalue problem, you have a wave that bounces back at a turning point, and you need to make sure they're in phase or whatever. This, to me, was unusual in that I had a turning point with a real decaying exponential that then reflected back and gave me the exponentially small stuff. So I hadn't seen that before, but other people have observed that, and I'm sure there are lots of problems like that around.
And this thing where the solubility is satisfied to all orders as well, is that unusual, or is that?
That's just because of the symmetry. So it's the fact that the term you correct with is even, and the thing you start with is odd. And so I think that will do it. So I think it's not hard to get that.
So with that, let's thank John. And I guess we'll invite you to coffee